This is the third video in a series devoted to differential equations. And in the previous video, we solved our first kind of family of differential equations known as first-order linear differential equations. And today we're going to look at another family of first-order differential equations known as separable differential equations. So let's look at the definition. So we say a first-order differential equation is separable if it can be written in the following form. We have y prime equals f of x times g of y. So this is a single variable function of x and a single variable function of y that we are taking the product of. So let's look at some examples and non-examples. So down this column we've got examples, down this column we've got non-examples. So here's an example of a linear separable differential equation, y prime equals y times e to the x. So that's clearly a function of y times a function of x. And it's linear because of things that we talked about earlier. And then a non-example would be y prime plus y equals 3x. Now you could rewrite this maybe as y prime equals negative y plus 3x. And then you have y prime is the sum of a function of x and a function of y, but not a product. So this is not separable. But we do know how to solve this using methods from the previous video. Then next we could have y squared equals y prime, or y squared times y prime equals sine of x. That is nonlinear, but it is separable. It's not in this form, but dividing by y squared could very quickly put it into that form. Another non-example that is nonlinear would be y prime equals e to the y plus e to the x. So again, that's non-separable and it's not linear. It's non-separable because we have a sum of functions of x and y, not a product. Okay, so let's talk about a general solution strategy here. And so this is maybe a really classic type of differential equation. In fact, if you've taken an integral calculus class, it's likely that you've learned this solution strategy. Okay, so let's say we are given a separable differential equation, f of x times g of y. And then I'm going to introduce a new function that's built out of y. So I'm going to set h of y equal to 1 over g of y. Okay, great. But now what does that do to my differential equation? That turns my differential equation into y prime equals f of x over h of y, which can be rewritten as h of y times y prime equals f of x. So it looks like we've got everything that looks like a y over on the left-hand side and everything with an x over on the right-hand side. And that really motivates us to define the following two functions. So let's define capital H to be an antiderivative of little h, and then capital F to be an antiderivative of lowercase f. And now let's notice if we take the partial derivative with respect to x of h evaluated at y, then that's in fact equal to h prime of y times y prime by the chain rule. But then that's going to be equal to, let's see, f of x, and that's by our differential equation here. But then that's going to be equal to the derivative with respect to x of capital F of x by the definition of capital F as an antiderivative. So let's notice that we can move some things around. We can take this extreme left-hand side and this extreme right-hand side and form the following equation. We have the derivative with respect to x of h of y minus f of x equals 0. But the derivative of something equals 0 means that something is a constant. So we have h evaluated at y minus f of x equals a constant, but I'm going to rewrite that as h of y equals f of x plus a constant. And now what we have achieved is an implicit definition of y in terms of x. And so let's write that down. This implicitly defines a solution, which I'll just call y of x. And sometimes you may be able to explicitly solve for y as a function of x, but other times you may not. So now that we've got this like sort of careful way of finding a solution to this differential equation, let's look at the quick and dirty way that you'll generally use when you're working through these calculations. So now that we went through our careful way of finding a solution to this differential equation, let's look through a fast and sketchy way. So we're starting with the same differential equation, y prime equals f of x times g of y. And now we're going to take y prime and rewrite it as dy by dx. So that's f of x times g of y. We're just changing the notation from Newton's notation to Leibniz notation. And now here's where the sketchy part comes in, is you're going to take this object, which is a derivative, and instead of viewing it as a derivative, you're going to view it as a ratio of differentials. So thinking of it as a ratio of differentials isn't maybe quite as sketchy as you might think it is. Okay, so that's going to give us dy over g of y equals f of x dx. So something like that. And now what we'll do is just take the antiderivative of both sides. We'll take the antiderivative of the left-hand side with respect to y and the right-hand side with respect to x, and then we'll put a plus c on there for good measure. And now we've got an implicit description of y as a function of x. Of course, you've got to take those antiderivatives. Okay, let's do some examples. So let's start with these two examples. We've got y prime equals x times y squared first. So that's very clearly in this format. So let's get to it. So like we did before, we'll take this y prime and write it as dy by dx. So we've got dy by dx equals x times y squared. I'm going to warn you, we'll use that sketchy method because in the end, it's equivalent to doing it that careful way. You essentially just find antiderivatives of two different functions, and that gives you your implicit description of y as a function of x. Okay, so we've got something like this. Now we can write dy over y squared equals x dx. Now we can take the antiderivative of both sides. So that's going to give us something like minus 1 over y for the left-hand side. Again, using the power rule, keeping in mind that we've got y to the minus 2 here. And then this is going to be 1/2 x squared plus a constant. Actually, maybe it would be a little bit better to write that as x squared plus a constant all over 2. You might say, well, this constant varies from the other constant by a factor of 2, but since that was an arbitrary constant, we can absorb it into the constant. Okay, now we can take the reciprocal and negate. That's going to give us y equals a constant minus x squared over 2. You might say, well, what about the minus sign in front of the c? Well, again, that's an arbitrary constant. So I'll just go ahead and absorb that into the constant. That's something that I'll do most of the time when dealing with constants in these differential equations, is absorb multiples of things into them as appropriate. Okay, so there's our solution for this differential equation. Now let's look at the second one. We have y prime equals 1 plus y squared times cosine of x. So that's going to give us dy over 1 plus y squared equals cosine of x dx. So I kind of skipped a step, but the only step that I skipped is writing y prime as dy by dx. Now we'll take the antiderivative of both sides. So that's going to give us the arctan of y on the left-hand side. And then on the right-hand side, that's going to give us the sine of x plus some constant. And now we can take the tangent of both sides, and that'll give us y equals the tangent of the sine of x plus a constant. And you know, that might be a suitable way to leave this, but we could also use the sum angle formula for tangent to work this out a little bit more. That'll give us something like the tangent of the sine of x plus the tangent of that constant. But just as you might have thought, I'm going to rename that c. And then this is going to be over 1 minus the tangent of the sine of x, and then times that same constant c. So just look up the rules for the sum angle formula for tangent, and you'll see that that does this step here, where, just to be careful, from one step to the other, I'm setting c equal to the tangent of c. And now we're at this stage. I don't think there's any simpler you can get. I think that's maybe as good as we can get for this. Okay, let's do a couple more examples. So here we've got another example. This one is an initial value problem. So we've got the square root of x times y prime minus the square root of y equals x times the square root of y. So there's in fact a little bit of work to do here to put this into the form that we have over here. So let's see, maybe we'll start by rewriting this as the square root of x times the derivative of y with respect to x equals x times the square root of y plus the square root of y. So now looking at that, we're motivated to maybe pull the square root of y out of this sum. That'll give us the square root of y and then x plus 1. And then furthermore, we're motivated to divide by this square root of x, so let's do that. We have divided by the square root of x, and that gives us our dy by dx. Okay, so let's see, that'll give us y to the negative 1/2 dy, dividing that square root of y, equals something like x to the half plus x to the minus half dx. And that's from dividing that x plus 1 by the square root of x using like rational exponents there. Now we can take the antiderivative of both sides. So this is going to boost the exponent to 1/2. And then we have to divide by the new exponent, but dividing by 1/2 is the same thing as multiplying by 2. And then we've got similar calculations over here. So this is going to give us something like 2/3 times x to the 3/2, and then plus 2 times x to the 1/2. Okay, and then plus a constant c. So we're left with something like that. And now let's clean this up a little bit by dividing everything by 2. And also we can factor a square root of x out of this left-hand side, a bit at least. So we're left with the square root of y, that's what we have for this right-hand side, is equal to something like the square root of x times x over 3 plus 1, and then we have plus a constant, where I've absorbed that division by 2 into the constant. Okay, so now we're ready to evaluate this at x equals 9 and y equals 4. That's given by our initial condition. So let's see, x equals 9, y equals 4. That's going to give us an equation for c, hopefully. So let's see, the square root of 4 is 2 equals the square root of 9 is 3. 3 over 3 is 1 plus a constant. So let's see, we have 2 equals 6 plus a constant. What does that mean that constant is? I believe that means the constant is -4. Okay, so that means we can plug that in up here, and we have the square root of y is equal to the square root of x plus times x over 3 plus 1 minus 4. And then to finish this whole thing off, we can square both sides, and that'll give us y equals the square root of x times x over 3 plus 1 minus 4 all squared. Okay, let's do one more simple example, and then we're going to look at some more complicated ones. So for our next example, we're going to look at the differential equation y prime equals half x times 1 minus y squared. Okay, so let's get started here. So the first thing that I'll do is write this as dy over 1 minus y squared equals x over 2 dx. So that's skipping a trivial step from before where we took y prime and wrote it as dy by dx. Now we're going to take the antiderivative of both sides, but honing in on what's going on right here, we see that we might want to use a partial fraction decomposition. So let's work that out real quick. We have 1 over 1 minus y squared must be equal to a over 1 minus y plus b over 1 plus y. Okay, so let's see, if we multiply this whole thing by 1 minus y squared to like clear the denominators, that's going to give us the following equation. So we have a times 1 plus y, and then plus b times 1 minus y equals 1. And that's because of the cancellation that gets done when you multiply into each of these. Okay, so now from here, let's notice that if we set y equal to the number 1, this bit cancels, and we're left with 2 times a equals 1, which means that a is equal to 1/2. And now let's notice if we set y equal to -1, Then this bit cancels and we're left with 2 times b equals 1. In other words, b is also 1/2. Okay, so let's see what that gives us. So that means we can take this version of our differential equation and rewrite it as the antiderivative of, let's see, we can bring a half out front, so 1/2, and then we have 1 over 1 plus y plus 1 over 1 minus y dy. Great. And then I'll go ahead and take the antiderivative of this right-hand side. That's going to give us, let's see, x squared over 4 plus some constant. So next, I'll multiply both sides by 2. That'll get rid of this half, turn this 4 into a 2, and then absorb it into the constant. But now we can take the antiderivative here. That's going to give us the natural log of the absolute value of 1 plus y minus the natural log of the absolute value of 1 minus y equals x squared over 2 plus some constant. But now we can use log rules to put this together. That's going to give us the natural log of the absolute value of 1 plus y over 1 minus y equals x squared over 2 plus some constant. We can exponentiate both sides. That'll give us 1 plus y over 1 minus y equals e to the x squared over 2 plus a constant. But now I'll use exponent rules on the right-hand side to write that as e to that constant times e to the x squared over 2. But then you guessed it, I'm going to rename e to that constant just equal to a new constant, which I'll also call c. Okay. But now we can solve this for y if we really want to. Notice cross multiplying, we'll get 1 plus y equals c times y times e to the x squared over 2. Then we can move everything with a y to one side of the equation, everything without a y to another side of the equation. That leaves us with something like y plus c times y e to the x squared over 2 equals c times e to the x squared over 2 minus 1. And then from here, we'll probably just factor a y out of this right-hand side, leaving us with 1 plus c e to the x squared over 2 equals c e to the x squared over 2 minus 1. And then the very last step will be to divide by 1 plus c times e to the x squared over 2, giving us a final value for y. I don't have room here, so just in the editor, we'll put it on the screen right now. And now let's look at one trickier type of example. So now we're going to look at a trickier example. So this is not separable, and it's also nonlinear. So it's nonlinear and non-separable. And a general rule is if you've got a nonlinear, non-separable differential equation, in order to be able to solve it, there's probably some trick. And that's because it's really easy to write down an impossible to solve differential equation. Okay, what do we have here? We have y prime plus y equals 2x e to the minus x over 1 plus y e to the x. And the fact that y and e to the x are coupled in this denominator gives me some sort of motivation that maybe our trick will be to view this y times e to the x as its own function. And that indeed will be a nice trick, because if we set z equal to y times e to the x and calculate z prime, then we'll get y prime times e to the x plus y times e to the x. But notice that's exactly this left-hand side multiplied by e to the x. So in other words, this is e to the x and then y prime plus y. So seeing that, along with the fact that y and e to the x are coupled right here, motivates us to multiply both sides of this equation by e to the x. So let's see what we get if we do that. So that's going to give us e to the x times y prime plus y equals 2x. With no e to the x, that cancels over 1 plus y times e to the x. Great. And now let's notice from our kind of exploration over there, we have this bit is what we called z, and this bit over here on the left-hand side is z prime. But making that substitution turns this into what is indeed a separable differential equation. So let's notice that doing that, we have z prime equals 2x over 1 plus z, which we can solve with separation of variables technique. So that gives us something like 1 plus z dz equals 2x dx, which means we have, let's see, z squared over 2 plus z equals x squared plus a constant. Okay. But now I'm going to multiply both sides by 2 to clear the denominators. And that's going to leave me with z squared plus 2 times z equals 2x squared plus a constant. Absorbing that 2 into the constant. But look at this left-hand side. It's almost like the square has almost been completed. In fact, if we add 1 here, then we can factor that. And then we'll need to add 1 to the right-hand side. But you guessed it, we're going to absorb it into the constant again. But now factor this and we get z plus 1 quantity squared equals 2x squared plus a constant, which means z plus 1 equals plus minus the square root of 2x squared plus that constant. But then we can subtract 1 from both sides. And we have z is equal to that, but then we can substitute back in and we really have e to the x times y is equal to that. So in the end, we have y is equal to plus minus e to the minus x times the square root of 2x squared plus a constant minus e to the minus x. And you might say, well, how do I know if I take the plus or the minus? Well, I'll just circle this real quick and mention that that's going to depend on the initial condition. So we won't really worry about it. In fact, I think maybe we'll just erase the plus minus and that will be a solution to this differential equation. Okay, so now we're going to move a little bit away from separable differential equations and look at a really important big theorem regarding the solution to a differential equation. Okay, so our big theorem that we're going to look at for today goes like this. We will not prove this. That's not really in the scope of these videos. So if we've got a rectangle in R2 that's defined by all values of x between a and b and all values of y between c and d, so you could also write that as the interval ab cross the interval cd, and we have a function which is continuous on that rectangle, and we have a point in that rectangle which I'll call x naught y naught, then the differential equation y prime equals f of x y such that y evaluated at x naught equals y naught has at least one solution on an open interval I, which is a subinterval of a comma b that contains x naught. So that's the existence of a solution given that this function defining the first order differential equation is in fact continuous in the right spot. And we have like some sort of initial condition that makes sense. I should point out that this could be a linear, nonlinear, separable, or non-separable differential equation. Okay, so that's the first part, when we are guaranteed the existence of a solution. Then the second part gives us some sort of reason when we can expect the uniqueness of a solution. And that goes like this. If, in addition, the derivative of f with respect to y, so the partial derivative, is continuous on that rectangle, then this solution is unique. Okay, so let's get to it with a couple of examples. So this first example, y prime equals x plus y over x minus y. So let's notice that we have f of x y equals x plus y over x minus y in this case. Great, and then also notice that this is going to be continuous on all rectangles, maybe R, that do not intersect the line y equals x. So let's get a little picture of that going on here. So let's see, this is our R2, good. And so the line y equals x is bad. I'll draw that in yellow. Great. And then as long as we have a rectangle that does not intersect y equals x, then we're okay. So that could be a rectangle like this. Maybe we'll put A here, B here, and then maybe C right here and D right here. So let's see, that's going to look something like this. It should be an open rectangle, so it does not include the boundary, but I won't write it like that. Maybe I'll shade it in blue to say that the blue part is that part that's included. So notice that rectangle does not hit our curve. So that means our function is continuous on this rectangle. Furthermore, if we take an initial condition, y of x naught equals y naught, so that would be like this. That would be our initial condition lies somewhere in there. Then we know that this initial value problem is, in fact, solvable. And notice it's always possible to find such a rectangle as long as x naught does not equal y naught, because we can just make that rectangle really tiny so that it will not hit the curve. So that means that this theorem is implying that there exists a solution for all x naught, y naught, such that x naught is not equal to y naught. Depending on how far x naught and y naught are from each other tells you how large your rectangle could be, though. Notice we could make our rectangle larger in this case up until the point where we would hit this thing. But that being said, we get a solution regardless as long as our initial condition does not lie on this line. Okay, so now let's go ahead and take the partial derivative with respect to y to see where we get uniqueness. And in order to take the partial derivative with respect to y, I'm actually going to rewrite this kind of in a nice way for taking the derivative with respect to y. I'm going to take x plus y and write it as 2x minus x minus y over x minus y. So notice if you were to simplify that numerator, you would get exactly x plus y over x minus y. But now let's notice that that gives us 2x over x minus y minus x minus y over x minus y, but that's just minus 1. But now if we take the partial with respect to y, we don't have to worry about the numerator here because there's no y's in the numerator. So the partial with respect to y will be negative 2x over x minus y quantity squared, just by like standard derivative rules. So since this is also continuous as long as x is not equal to y, that tells us that this solution is unique. Okay, so now let's look at an example where we're guaranteed a solution, but maybe not a unique one. Okay, so for our next example, we've got this separable differential equation, y prime equals 10/3 x times y to the 2/5. Our initial condition is y of 0 is 0. So let's notice that in this setup, our function f of xy is 10 over 3x times y to the 2/5. Let's also notice that this function is continuous at 0, 0. In fact, it's continuous in a rectangle around 0, 0. But by this theorem over here, that guarantees that we have a solution on some interval containing 0. But now let's look at the partial derivative of f with respect to y, and notice just by the power rule, that gives us something like 4x over 3 times y to the 3/5. The important thing here is we have a y in the denominator. The fact that we have a y in denominator, that means that this is not continuous at 0, 0, because we get funniness at the origin. So that means that even though we are guaranteed a solution, that solution may not be unique because we don't satisfy this last sentence here. Okay, so we'll actually show that we do have a solution and it's not unique by giving two solutions. So let's first notice that there's a really simple solution that we can write down, and that is the solution y equals 0. Or in other words, y evaluated at x equals 0 for all x in the real numbers. That's most definitely a solution. So let's write that down. Is a solution. It's maybe not a super satisfying solution, but it is a solution. Okay, so let's maybe use separation of variables to see if we can find another solution. So notice that doing our standard separation of variables strategy here, we would get something like dy times y to the minus 2/5 equals 10 over 3 x dx. then we can integrate this. So let's see, taking the antiderivative of both sides, one with respect to y and one with respect to x, we would get something like this. 5/3 y to the 3/5 over here on the left-hand side. And on the right-hand side, we have 5/3 x squared plus some constant. But now let's go ahead and evaluate this at 0, 0, and notice that that tells us that our constant is in fact equal to 0. So that means we can just cancel this 5/3 from both sides of the equation. We can raise both sides of the equation to the power 5/3 to cancel that 3/5, and we'll end up with the solution y equals x to the 10/3. And that is a second solution to this differential equation, or this initial value problem. So we indeed saw that we do need this second condition in order for uniqueness of the solution, because here's an example where we do not have that second condition and we do not have uniqueness of this solution. Okay, so I'm going to leave you guys with a couple of warm-up exercises. So here are 4 warm-up exercises to practice based on what we did today. So the first is a separable differential equation. We have x times y prime plus y squared equals y. The next is y prime plus x times the quantity y plus y squared equals 0 with an initial condition of y of 2 equals 1. Next, we've got y prime is 1 plus y squared over 1 plus x squared. And then finally, we've got a nonlinear, non-separable differential equation, x times y prime minus 2y equals x to the 6 over y plus x squared. And since it's a nonlinear, non-separable first order differential equation, that means there must be some sort of trick or substitution that we can use that will turn this into a first order or a separable differential equation. A first order linear, I should say. And in this case, I think the substitution z equals y over x squared fits the bill. And that's a good place to stop.